Yeah, this is the final slide to give you some understanding about the flow convection acting on the liquid droplets. And this is a very interesting experiment since we want to see the growth of the wave frame downstream of your droplets. Now we try to have a larger scale to think about how the recirculation zone or wake region inside of your wake frames. Then we try to develop an experimental system. This is the small wind tunnel, actually the flow moving upward from the lower panel. Here we have a honeycomb and screens to produce a uniform gaseous flow moving from the base of your the wind tunnel and flowing upward. Okay, and in this region, there is the combination of two semi-cylinder. The two semi-cylinder, the upper cylinder actually is a solid cylinder, but with a slot. You can see this is the upper one. There is a slot, and we insert some sponge in, and for this upper full semi-cylinder, actually we supply the liquid fuel from the side wall. There is a tube connected to the to into the this semi solid cylinder, and here the flow liquid flow will move and to the slit, and they will they will go through the sponge and overflow from the surface of the cylinder. That means that you will produce the liquid liquid fins on the cylindrical surface or the cylinder surface. Okay, and those liquid will flow from they will move out from the sponge and flow along the surface of a cylinder. Then they will flow to the loader cylinder, and the loader cylinder is the hollow cylinder. Here this is empty. Okay, actually they just act as some kinds of they can restore, they can allow the liquid fuel flowing into into your loader cylinder, and those liquid fuel will be drawn out by the other tube. Okay, the mechanism is as simple as like this. We supply the liquid fuel from the upper semi solid cylinder through the sponge, and those liquid fuel flowing out, and basically they just can have a very thin liquid film and flowing along the surface of the cylinder. Then they will flow to the downstream to the lower empty, the hollow semi cylinder. The size of your the cylinder, the loader cylinder has a smaller, has a larger, maybe just a small, larger 1 millimeter thickness, larger than the upper ones. Then those kinds of liquid fuel will flow into the hollow semi cylinder. Then they will flow out by another tube. Okay, which means you will have a cylinder and then you provide a liquid fuel continuous moving out to wait or to moving along the cylinder surface. Actually, this tell you is just like the liquid surface can be used to describe the liquid surface of a cylindrical droplet. Okay, and in this sense, we can apply the water, the air coming from the lower part, and those flow convection were acting on those kinds of liquid fuel. Initially, you can see if you have a liquid fuel flowing out from the sponge and waiting on the liquid on the cylinder surface, then you ignite it, then you can have a very nice diffusion flame. Actually, this is a typical one when the flow velocity is very small. It's 0.47 meter per second from the upstream side. You can see there is a flame exists. You can see this is the attached boundary between the upper, this is the upper cylindrical cylinder, and this is a lower cylinder has a slightly large diameter radius to allow the liquid flow in and to be accumulate, okay, and draw out. And when you ignite it, you can see there is the blue flame exists. This is a very nice diffusion flame. Then you have a wet flame here. Okay, this flame is basically similar to the. You can see this is a. You can treat as a spherical droplet, right? And here you can see the flame extends in the downstream of your liquid film. When you continue increase your flow velocity, you can see that the flame length. Okay, the flame length in the downstream side is continuously increase to a certain value that start to reduce. Okay, especially when you take the picture, enlarge it, and study it, you can see as velocity go to the 1.81 this case, and 1.95 I enlarge it, and you can see this very nicely. You can see since in your diffusion flame there is some subparticle, right? Subparticle is a good seeding when for our visualizations because they will emit the yellow color to tell you the motion, right? Then you can see very clearly there is the recirculation zone here, right? There is a recirculation zone here. But definitely you will ask why they are not symmetric. This depends on do we have a particle moving into the circulation zone. Just I explained earlier, when you apply the magnesium oxide into your flow circulation regions. Sometimes if those kinds of particles cannot make it, cannot enter the recirculation zone, you cannot see the motion. Okay, but those kinds of is a temporary and it's very dynamic. When you have a long observation, you will see there is a symmetric pair of a recirculation zone. This is a very nice picture to tell you. You may have those kinds of mechanisms for droplets, as we see from the free falling droplet experiment. Droplet size very small, but you believe they still have a small AD exist in the downstream of your droplet. They have some recirculation zone. If you increase your velocity further, you will find out the flame cannot be stabilized where there is some flame already have some dip off since they cannot stabilize in the near the edge of your cylinder. Tell you they have a possibility to be dip off. In this sense, since the certain flame is already disappear, there is a hole allow the air coming in. Then you can see the yellow color is complete diminished for the case of 2.65 meter per second. This experiment just give you some observation experimentally to look at the possibility of recirculation zone exists in the downstream of your diffusion flame. And this is a very nice experiment. But up to now, people will think about, yeah, this is a very good question to think about. Do we need to consider the droplet burning in the real application? As I mentioned to you, for the droplet, because the most important thing is in the combustion process, the gasification of droplet become the most important part. But for the liquid, for the droplet itself, vaporization in the hot temperature region or in the flame, the diffusion flame case, actually for droplet itself is almost the same, right? That means that when you go to the spray combustion field, there's so many droplets. This droplet may experience evaporation only, but this droplet is enveloped by a diffusion flame. Do we have any difference between these droplets for turbulent mixing a spray flame? Because inside of the droplet, inside of the spray field, actually they have some, the mixing is very strong. There is some reaction, there is no reaction, but still have temperature high. Okay, the temperature difference do not change too much. In these regions, actually droplet experience the same thing. They experience the same hot temperature from the purely hot temperature environment without flame and with flame. They have the same feeling, which means when you look at the droplet itself, then we need to ask the same problem. Do we need to bring the combustion model into your spray simulations? Yeah, now this is a good questions arise for in the literature. People will think about maybe we just need to think about the evaporation of droplet in a high temperature is good enough without consider the diffusion, the droplet diffusion friends mechanism. Okay. Now we change it to our subjects. Let me try to switch it. Sorry. Sorry, I cannot. Okay, now give me a time. Sorry. We go back to our lecture notes. We will switch because we already finished the discussion on the single droplet combustions, especially we consider the pure substance up to now. Now we need to have some introduction on a very important application for spray burning. That means that we are looking at the so-called multi-component droplet combustion, and you can turn to your page 2.9. Okay. Now we think about if our liquid droplet is not a pure substance, they mix a different component together, then what happen? You may have. Now let's look at the first group, and we say the so-called miscible field brands. Miscible field brands means you bring these two components together and just mix it, and very nicely they will make a new component droplet. But the other one, immiscible, that means that you need to have some surfactant to make these two components or species together. Oh, okay, this is a simple say that miscible fuel blend means that those kinds of liquid fuel has almost a very similar property, and they are easily to be mixed. Where okay. Now, when you mix two or three different kinds of liquid fuel together as a new brands, then you will need to look at the important thing for so-called Lewis number. We already mentioned Lewis number for gas phase combustion are quite important because they are talking about the balance between the thermal diffusion and mass diffusion in the near the in the preheating zone of your premise frame. Okay, and also for the for both sides of diffusion frame because those diffusion process control near the frame are quite important, need to be considered. But for liquid surface or for the liquid, yeah, it is very interesting to think about now. We are dealing with the different components liquid, right? Not a pure substance, which means if you have a two component of liquid mixed together, then those kinds of mass diffusion occurs inside of the droplet, right? A and B, two component of fuel. A will diffuse to the B side. B component will diffuse to the A side. If you do not mix well, those kinds of mass diffusion process will occur, and you need to consider the so-called mass diffusion inside of your liquid droplet. Okay, but you need to think about for the liquid if you consider the definition of the Lewis number for liquids, they still tell you the thermal diffusibility divided by the mass diffusibility, right? Which means for liquids, you are thinking about the heat transfer coming from the outside, right? Then heat will transfer from the surface to the interior of the liquid. That means that this is a so-called heat diffusion in the liquids. Usually, people will tell this is a so-called the heat conductions. This is another terminology, but heat diffusion is in general can be used for the liquid and also for the gas. Okay, and the other transport you need to consider is mass diffusion because now you have two components, A and B, and those components maybe they have a very similar thermal properties, but they still have some difference. And what will happen you need to be considered when you think about the thermal diffusion and the mass diffusion for the liquid fuel. Easily to think about for thermal diffusion because all the component, all the molecule inside of liquids will transport the thermal, right? They have the same characteristics, but for the mass, they should not be the same because the mass depends on the motion of the two component molecule, right? And for the liquid, in compared with the gas, the separation distance between the liquid molecule is very limited. Then it is very hard to transport the mass inside of liquid in compared with the gas environment. In a gas environment, because the molecules are separate, has a larger distance, this empty space that the droplet that the molecule can pass in through, or they may interact each other, then the mass still can be transported easily by diffusion mechanisms. But for a liquid, actually mass diffusion is very difficult compared with the thermal diffusion. Therefore, the Lewis number for Lewis number is much larger than 1. Much larger than 1, that means it represents the mass diffusibility in the denominator is very small compared with the thermal diffusibility in the numerator. Okay, then the value for Lewis number in liquids is much larger than 1. Now, is this important for the multi-component droplet burning? It is did. It is important too. Then you can see let's exempt a mixtures of two liquid fuel. Is one is a decant, the other one is a dodecane. I tell you when you choose this is just a theoretical prediction to let you know the variation of concentration and the temperature inside of the droplet as this droplet is burning. Okay, and they use two components. One is a decant, the other one is a dodecane. They have a very similar thermal dynamic properties, but decant has let me see, has a high decant has the lower boiling point. Okay, and the boiling point is around 447 K, but for dodecane has a higher boiling point is 489 K, but the difference is not too much, around 50 K. But those kinds of difference in boiling point, you will figure out when they mix well together, and this droplet will experience the outer flame, right? And those heat will supply to the this multi-component droplets, and you will figure out the evaporation will start based on the boiling point, and you realize in the evaporation process or droplets, definitely decant will start to evaporate earlier than the dodecane. Okay. And this simulation will tell you if you mix this decant and dodecane by 50%, okay, then this figure tell you the concentration of one of the decant, one of the component decant, okay, and the change with the M represents the how much mass they evaporate. Okay, you can treat it as the time change. Okay, starting from the 0, time is initial time, and finally they finish their gasification. And at the initial time, actually the no more fraction for decant is 0.5. That means 50%. The other 50% will belong to dodecane. Okay, and they try to give you the explanation on the variation of the decant concentration on the surface of the droplet and also at the center. Okay, this is a concentration distribution, and they also calculate the temperature distributions. Okay, here the same way the horizontal axis represent the time history. Okay, how much the fuel evaporates until one means the droplet is complete, finish the gasification. Then in this period, they measure the droplet temperature on the surface and also at the center point. Okay. Now the interesting thing is, okay, look at the concentration distribution variation. Initially, they have a 50% thicken and a dot thicken for the whole droplet. But when you ignite it, it has a diffusion frame surrounds on this two components field. You will find out for the thicken I mentioned, since the thicken has the lower boiling point, then on the surface, on the liquid surface, they can start to evaporate very fast. Then in the initial periods, if you look at the surface area, you will find out the concentration of thickening drop very fast. Okay, but around m equal to 0.4, actually the decrease of concentration, that means the evaporation of the thickening has become lower. Okay, they maintain a certain amount of a certain concentration without too much change. Okay, and here you can see at the center, actually starting from the beginning to the end, actually the composition of your thicken and dodecan almost no change. In this case, they tell you in the initial transient period, the thicken concentration near the surface is rapidly depleted owing to its volatility. Then, since I already mentioned, thicken has a lower boiling point, then they will start to evaporate very fast. But at certain point, the thicken on the surface completely evaporates. Then they just have some thicken left, okay, which means we need to wait a little bit heating to make a thicken has the higher temperature to reach its boiling point and to start to burning. But in this case, you will find out the the concentration on the surface is limited by the transport of the dodecane from the center positions to the surface. Okay, they tell you the intermediate mass diffusion limit process basically is a steady state. Since here the mass diffusion in the liquid phase is very limited, you cannot transport the thickening from the center to the outer surface efficiently. Therefore, you will keep the same condition. Almost you do not you already burn out most of the thickening. Just have maybe 25% left, 75% thickening absorb heat for their temperature increase. Okay. And this kinds of behavior, the steady state situation extend further even to the end of the droplet lifetime. Okay, now here there is a so-called final volatility limit period, because here they tell you that basically in this period is controlled by the higher boiling point dodecane. Okay, but for the temperature distribution, now you are surprised that in the previous part to tell you, we have a difficulty to transport the thickening from the center portion to the surface. But for the temperature, you will find out initially, okay, the center temperature is low, the surface temperature is high, definitely, because you still need to have a time to transport heat to heating up all the droplets. But those kinds of temperature for the surface of the mother component droplet and also the temperature inside of the droplet, you will find out initially they have a temperature difference, and the surface temperature initial is governed by a lower boiling point thicken, but when they reach to the 447 around here, and they will find out they will continue to increase because the intermediate periods they were limited by the higher boiling point, which means it's a 489 K boiling point for the dodecane. But in this period, you will find initially there is a big difference between the temperature on the surface and at the center. But those kinds of difference will reduce when they move to the around 0.5 and the middle time of the droplet life. Then you will see the surface temperature is almost the same with the center temperature. They tell you in this period from 0 to m equal to 0.5, okay, here 0.5, they give you they exist a big concentration difference for given field, but for temperature for the old droplet, actually they almost no difference. And this tell you the big difference for the mass diffusion. Okay, mass diffusion is almost is very weak compared with the thermal diffusion. Okay, here this is the comments. They say the droplet temperature is controlled by the loading point of the volatile component at the initial state, as I mentioned. Okay, but controlled by the high boiling point of the less volatile component for the steady state period. That means it's controlled by Droplet. Okay. Now, when you uh, this is this was justified by theoretical predictions to let you know the inference coming from the Lewis number on liquids, and they tell you mass diffusions is much less than the thermal diffusion, and this is a very interesting mechanism need to be applied for real application. I will tell you. But since those kinds of mechanisms is limited by the mass diffusion transport, and they still show you they can maintain a concentration difference, which means for they can have a 50% in at the center and 25% at the surface, and continuous remain constant until the end of the droplet lifetime, which means in this case, they tell you the droplet actually is well mixed by the decan and the top decan. And in this period, the steady state period, decan always has the 25% concentration on the surface and 50% at the center. They do not change. And when they do not change the composition, which means the burning will be steady. Okay. Now the experimental result will give you the justification here. This experiment they use the undecaned. Let me give you the boiling point. Undecaned is a 469.1 K, 469 K, and octanol has 468 K. The boiling point is almost the same. Then when they mix it, then you can find out, yeah, they do the very nice d squared law, because the composition almost actually in this case the boiling point they are almost the same. They look at just like depends on if you look at the gasification, they just like a pure substance. Then you can have a very nice d squared law linear curve. You can expect it. But when you change to do the experiment with large boiling point differences, there is the carbon 7 and the carbon 16, these two fields, and you can mark it for the boiling point for C7 is around 209 Fahrenheit, and for C16 is almost double, even double, 548 Fahrenheit. Is much higher boiling point for C16 compared with the C7. Then what's happened? You will find out in the experiment. They tell you if you mix just a small amount high boiling point fuel C16, this is a 10%, then you increase to 40% to 80%. Then we try to do the measurement for the droplet size variation, depends on the d squared law. Okay, for the first case, case A, you just have a small amount of the high boiling point C16, and you will find out in the earlier, even in the middle lifetimes of your droplet, you can fit very well with the d squared law. Basically, in these periods, the burning of these multi-components basically is controlled by C7, but there is some kinds of a change occur here. Okay, they were lower the, since you initially you can have a larger gradient of temperature, right? a larger gradient of a d squared of k represent the gasification constant is stronger. But here there is they show you a shadow change of your droplet. That means in this case, in these regions, since most of the C7 already evaporate, then you need to face a more amount of the C16s, but 16 has a double, higher than double of the boiling point. Then you need to wait heat sufficient to increase temperature to meet the boiling point required for C16 gasification. In this case, the droplets do not change too much. They remain almost a constant radius. In this case, when you think about the droplet size do not change, actually this environment, this situation tell you the droplet absorb heat for heating. Okay, now you can see there is a small change for droplet diameters, and they're waiting for the heating on the C16. Later on, you will find out they will continuous follow the linear curve, this square law. Okay, this is the inference coming from the 10% 16 field, and with the inference coming from the much higher boiling point. Now, if you increase the concentration of 16s to up to the 40, then you will find out this the flat variations on the droplet size become more severe and occurs in the earlier stage here. And in this stage, you can see the droplet diameter do not change too much. It just decrease by a small value. But at these times, you can see originally the diffusion frame exists for these droplet burnings. They almost look at certain positions. But in this period, droplet size do not change too much. But you find out the frame will become smaller. This is the so-called frame shrinkage phenomena. Why the frame becomes smaller? Since in these periods, all the heat used for heating, they do not have too much vapor coming out to support the diffusion frame. Therefore, the diffusion frame will move closer to your droplets. And you can see the frame radius becomes smaller. Frame shrinkage behavior occurs in this region. Okay, this is basically coming from the inference of the high boiling point C16. If you increase the more C16 up to the 80%, this platform shape will move closer to the initial periods and make this curve. Actually, become more like a curved line, not a linear line, right? And this is tell you some heating get involved with the gasification of the C7, and this become more curve, do not have a linear variation. Okay, and this experimental observation gives you some insights on the influence of the two different components of liquid fuel. If they do have a different boiling point and has a big difference, then you will find out the heat diffusion has a strong influence on the Lewis number effect of Lewis for the liquid will be bring to our attention, and those kinds of ideas give us to think about a very interesting behavior. We call it micro explosion mechanism, and we will explain it later.